Okay, the last lecture we have discussed different windows for designing of FIR filter. In this lecture we will discuss another method called frequency sampling for designing of FIR filter. But before we will discuss advantages and disadvantages of windowing method. So the first we will discuss the advantage. The windowing technique is very simple to apply and simple to understand. And then we have disadvantages of windowing technique, which can be distributed into two parts. First disadvantage is the peak side lobe to main lobe ratio and stop band attenuation is fixed in all windows except Kaiser window. That is the first disadvantage of the windowing technique. Second one is ripples in pass band and stop band are nearly same. In actual case, we doesn't want these ripples, and if these ripples should come, they should be very small in pass band. Now we will discuss frequency sampling method for designing a linear phase FIR filter. Frequency sampling method, and that FIR filter should have a linear phase. Now the process of designing an FIR filter using frequency sampling method will be divided into multiple parts. The first part is to specify desired frequency response HD omega at an equally spaced frequency. This particular process will lead to two types of FIR filters, namely called type 1 and type 2, where type 1 filters are those filters in which omega is equal to 0 is one of the sampled frequency, whereas omega is equal to 0 is omitted in type 2 filters. For this particular lecture and this course, we will discuss only type 1 FIR filter for this particular technique, which is called frequency sampling method. Now, to start with the frequency sampling part, first we will find out the frequency domain representation of Xn by using Fourier transform. That is given as x omega is equal to n equals to minus infinity to infinity xn exponential minus j omega n. We know x omega is periodic, thus we can sample x omega from 0 to 2 pi, and we can take m equidistant samples from 0 to 2 pi. Then the frequency, which is defined from 0 to 2 pi, and now if we sample this frequency by m equidistant samples, then frequency space between two samples will be delta omega, and it will be equal to 2 pi by m. So now we can define omega k, which is equal to 2 pi k by m, where this k will vary from 0 to m minus 1. That means all the frequency from 0 to 2 pi are covered with this changing value of k. Thus this omega k is the sampled frequency. Then substituting omega k in the Fourier transform will be x omega. Omega is now 2 pi k by m. Summation n equals to 0 to m minus 1 xn exponential minus j omega n, where this omega is 2 pi k by m. So then this x 2 pi k by m can be written as xk equals to n equals to 0 to m minus 1 xn exponential minus j 2 pi k by m. Now this equation is nothing but a discrete Fourier transform, also called DFT. Now this omega can be further modified as omega k is equal to 2 pi by m k plus alpha, where k is equal to 0, 1, 2, 3 up to m minus 1, and alpha is equal to 0 or 1 by 2. Now this alpha's value will define either it will go for type 1 or type 2. In this case we are dealing with alpha is equal to 0, as we are dealing for type 1 filter. Now our target is to solve for unit sample response Hn of the FIR filter from this Wk, that is sampled frequency. In that particular part, first point is to reduce the side lobes. Side lobes can be reduced by optimizing the frequency response in the transition region, and we know that the sharp transition in frequency region will give rise to side lobes in the time domain. So this particular process can be achieved by optimizing using digital computers and linear programming. Second point, for the designing of FIR filter using frequency sampling technique is utilization of the symmetric property of the FIR sequences. Now in this case, we'll try to emphasize over the symmetric property of the linear phase FIR filters. We know for HD omega will be equal to n equals to 0 to m minus 1 HDN exponential minus j omega n. It is gone up to m minus 1 because we have performed frequency sampling for m samples. Taking omega k, substituting omega k is equal to 2 pi by m k plus alpha will give HD k plus alpha equals to n equals to 0 to m minus 1 HDN exponential minus j 2 pi by m k plus alpha into n, where HD omega k can be written as HD 2 pi by m k plus alpha, can be written as HD k plus alpha, and k will vary from k equals to 0 to m minus 1. Now for the values of alpha, if we substitute alpha is equal to 0, then we will get HDK equals to n equals to 0 to m minus 1 HDN exponential minus j 2 pi by m kn, which is nothing but the DFT of HDN. Then we can utilize some of the properties of DFT, such as if we put HDK is equal to n equals to 0 to m minus 1 HDN exponential minus j 2 pi n k by m, then HDN minus k can be written as n equals to 0 to m minus 1 HDN exponential minus j 2 pi n m minus k by m. Then the resultant will be n equals to 0 to m minus 1 HDN exponential j 2 pi n k by m and exponential minus j 2 pi n. Now this exponential minus j 2 pi n can be written as cos 2 pi n minus j sin 2 pi n, where sin 2 pi n will be always 0 for any value of n, whereas cos 2 pi will be 1 for any value of 1. So that's mean this HD m minus k can be written as n equals to 0 m minus 1 HDN exponential j 2 pi n k by m, which is, now if we take conjugate both sides, then HD conjugate m minus k will be equal to n equals to 0 m minus 1 HD conjugate n exponential minus j 2 pi n k by m. Now for the case HDN a real sequence, then HD conjugate m minus k will be equal to n equals to 0 to m minus 1 HDN exponential minus j 2 pi n k by m, which is nothing but equal to HDK. That's mean we can relate HD conjugate m minus k with HDK as HDK is equal to HD conjugate m minus k. This is one of the most important property which we will use in frequency sampling method. Next part is we have to find out the impulse response of the FIR filter, that is HDN. Now HDN will be equal to inverse DFT, that is 1 by m k equals to 0 m minus 1 HDK exponential j 2 pi n k by m, where n varies from 0 to m minus 1. Now if we expand this expression, it will give 1 by m HD0 plus HD1 exponential j 2 pi n by m plus HD2 exponential j 4 pi n by m plus up to HDM minus 2 exponential j 2 pi m minus 2 by m into n plus HDM minus 1 exponential j 2 pi m minus 1 by m into n. Now by using the property of HDK is equal to HD conjugate m minus k, we can find out HD m minus 2 will be HD conjugate 2, and exponential j 2 pi m minus 2 n by m can be written as exponential j 2 pi mn by m into exponential minus j 4 pi n by m. Now this m and m cancels out, so this terms will be exponential j 2 pi n for now any value of n that starts from 0 to m minus 1, this term will be always equal to 1. So similarly we can apply the same property in this part, so it is at HD conjugate 1, and this expression will just solve into exponential minus j 2 pi n by m. Then the expression can be rewritten as 1 by m hd0 plus hd1 exponential j2 pi n by m plus hd conjugate 1 exponential minus j2 pi n by m from here, and then hd2 exponential j4 pi n by m plus hd conjugate 2 exponential minus j4 pi n by m from here, and so on. Now this expression can be written as 1 by m hd0 plus k equals to 1 to m minus 1 by 2 hdk exponential j2 pi nk by m plus hd conjugate k exponential minus j2 pi nk by m. Please note that this equation is only valid for odd sequences. For even sequence, it is equal to 1 by m hd0 plus hd m by 2 plus k equals to 1 to m by 2 minus 1 hdk exponential j2 pi nk by m plus hd conjugate k exponential minus j2 pi nk by m. Now this hd m by 2 will be 0 for the symmetric sequences. Then this equation will be reduced to 1 by m hd0 plus k equals to 1 to m by 2 minus 1 hdk exponential j2 by nk by m plus hd conjugate k exponential minus j2 by nk by m. Now we know the condition that hn should be real, because this particular property of hd conjugate comes only when hn is real. Then we can rewrite this equation as hn equals to 1 by m hd0 plus k equals to 1 to u hdk exponential j2 pi nk by m plus exponential minus j2 pi nk by m, which can be further solved to 1 by m hd0 plus 2 k equals to 1 to u hdk cos 2 pi nk by m, where this u is the point which will separate odd and even sequences. So u will be equal to m minus 1 by 2 for odd m and m by 2 minus 1 for even m. Now we have determined the impulse response of the filter in time domain. Also want to see the phase representation or the sequence, which can be written as hk is equal to mod hk exponential angle of hk, which can be written as mod hk exponential j theta k, where this theta k should be linear phase to meet with the requirement of linear phase FIR filter. Then we can put that particular condition which we have read in the previous lectures, that is theta omega at omega is equal to omega k will be equal to minus t omega at omega is equal to omega k. Then theta k be written as minus t omega k, where omega k is equal to 2 pi k by m. Substituting the value of omega k will give minus t 2 pi k by m. Now we can also substitute the value of t, which we know for linear phase filters is t equals to m minus 1 by 2. Then theta can be written as minus m minus 1 by 2 2 pi k by m, and for the solve to minus m minus 1 by m pi k 0 to m minus 1. One thing to be noted, that magnitude response is even function and phase response is the odd function. Magnitude response is even function, phase response is odd function. Then hk will be equal to hm minus k for 0 to m minus 1, and phase part will be theta k equals to minus theta m minus k, as phase is the odd function. Now we will try to find out the value of theta m minus k. So by replacing k to m minus k, we will get theta m minus k equals to minus m minus 1 by m pi m minus k. Now if we will solve this equation, we will get minus m minus 1 pi plus m minus 1 by m pi k.